Okay, welcome. My name is Walker Rowe. Today we're going to talk about tiling. Okay, most people think that GPUs are about parallelism, and they are. But that's not actually what limits performance. When people start writing CUDA code, tutorials and so forth, they focus on parallelism, how many threads to launch, how to structure blocks. But in practice, the performance is not limited by compute, the ability of threads to compute. The real bottleneck is memory access, meaning how often do you go back to global memory data. Shared memory is, each thread repeatedly loads the same data from global memory, even when neighboring threads need the same exact data. Okay, this creates redundant memory traffic. And since global memory has high latency, the GPU spends time transferring memory back and forth. So that's kind of time wasted, right? Okay, tiling fixes this. Okay, instead of independently accessing global memory, in tiling, threads cooperate to load a small amount of data into shared memory, which is much faster since it's loaded on the chip. It can be reused many times. So load once, reuse many times. That's the core idea. Okay, here you have a diagram showing the GPU, the blocks in the shared memory, and the registers. Remember, blocks are a collection of threads. Okay, so a thread block is a group of threads that share memory. The threads within the block can access shared memory, while all blocks access global memory, right? Okay, so here's what you do in a naive access pattern. So one thread computes one element, right? You have a dot product, produces a scalar, multiply two vectors, row, column, produces a scalar. Okay, now, so the same values from A and B are being loaded over and over again by different threads, right? Because A and B are the matrix that we're working on. We repeatedly load, for example, column 1, row 1, column 1, row 2, so forth. So we loaded column 1 2 times. Okay, we compute one element of the output matrix per thread, a dot product. Okay, inside the loop we load a value from A, we load a value from B, we multiply and add to the accumulator. Okay, each iteration pulls from global memory. Okay, each thread reloads the same data over and over. That's an area where we can see that there could be some boost in efficiency. Okay, global memory access is slower than shared memory access. So this creates unnecessary memory transfer traffic. Here's a diagram. It shows the basic concept of tiling. It's not complicated. You take an original matrix, break it into smaller sections called tiles. Work on each section at a time. Okay, so tiling changes this. Instead of every thread loading its own data, threads cooperate to load a block once into shared memory and then reuse it. Okay, we break matrices into smaller blocks called tiles. Each block maps directly to a tile. Each thread loads one element into shared memory. Now the tile sits in fast on-chip memory. Doesn't have to reach out to global memory. All threads in the block can reuse it without going back to global memory. So here's the basic loop. Mechanism, the computation loop looks like this. Okay, you load a tile into shared memory. Synchronize. Synchronize means so that all the threads have an up-to-date copy of it. Compute the partial results. Synchronize again, for the same reason, then repeat for the next tile. Adds to the final result. Okay, so let's take an example here. Let's look at a HD video image. You know, the image basically is height times width, and then there's one for each channel, red, green, blue, and then there's one for each time segment. So we'll just look at one image. So we're going to calculate a forward pass, right? That's what you do in AI, calculate forward passes, then pass off to different layers of the neural network, calculate softmax, repeat over and over. So here, the input layer, we have 1920 by 1028. That's the height times the width times 3, one for each channel, red, green, blue. That's about 6 million values. Okay, we can divide this into tiles. We just pick an arbitrary number. Each block computes one tile of the output. Okay, each thread computes one element. Again, the dot product. Okay, here's how CUDA maps tiles. You're familiar with this if you've already written a couple CUDA programs. So basically, block IDX shows which tile. Thread IDX shows which position inside the tile. Calculate row and column. Here we define the kernel launch. We define the block size and the grid size. And the next slide will show how to calculate the grid size. Okay, so in this example, each block is size 16 by 16. That's the tile size that we picked. Each block computes a 16 by 16 portion of C, the final output. Okay. So here, the next slide. Okay. So if we have N, which are the columns of W, that's our weight matrix, right? That's the number of neurons per that hidden layer in the neural network. Okay. Here we have the matrices W, Y. Y is that output that we showed. 129,600 in the Y direction, right? X is 4, Y is 129,600, being the number of pixels and number of channels divided by the tile size. Now we did some benchmarking here. NVIDIA GeoForce card in it. So the naive implementation, we're going to compare that against the tiled implementation, and then what I'm going to show you next is optimized tile implementation, where each thread will compute not one but 4 values, and we'll see how that works and why we use 4. Now then we have the tiled example that we just talked about. Okay, we get a kind of a moderate 35% boost in efficiency. And then we're going to do next the optimized tile. Okay, and that's a 3-fold boost in speed. Okay, now here's what I'm going to call the textbook versus production CUDA. Okay, the key change is quite simple. In the optimized code, each thread computes 4 outputs instead of 1, instead of a scalar. That might sound kind of simple and logical. It basically is. Okay, so each block computes, so each thread is responsible for 1 column and 4 rows in that column. K is the index along the inner dimension when you do matrix multiplication. Okay, so why did we pick 4 and not 8? Well, it's empirical observations coming from performance engineers. It's a trade-off. See, with 8 you need more registers, which means fewer active threads. So we're trading a little bit more work per thread for a lot less memory traffic. And 4 is a trade-off that works well in the field based upon observation.